viewers who are not members to consider joining. The membership cost remains at £20 sterling, 25 euros for a single, £25 sterling and 30 euros for a family membership. You can join through the website or via PayPal, which we would encourage as it's simplest all around. As Paul has already explained, we'll keep questions to the chat feature, and at the end of our guest talk, I will select a number of them. And as Paul has also explained, we will be staying on afterwards, and we can have a discussion of indeterminate length. That's it. Of the opening announcements. I'll now introduce our visiting lecturer, Professor Peter Ferguson, who is the head of IFAS and is accordingly one of the most, if not the most senior astronomer in Ireland. He's been largely responsible for getting the I-LOFAR project up and running, and we look forward to hearing all about it. So over to you, Professor. Thank you.
All right, thank you very much for the introduction. So hopefully everybody can see my slides. Danny, can you see that okay and hear me okay?
Yes, that's fine.
Great, great. All right, well, thank you very much for the invitation. I was really looking forward to making a trip back up to Belfast. I did my master's degree in Queen's and I did my PhD in Queen's, and my wife also did her PhD in Queen's. So we have a long connection to Belfast, and actually my father's from Fermanagh, if you really want to know the whole family history. So a big connection to Northern Ireland. But today I'm going to tell you about, actually it's a little bit of a life story for the past decade, plus also a little bit of astronomy as well thrown in there for good measure. And I'm going to tell you the story of building a radio telescope at Birr Castle, and also the first observations that we've been taken with that radio telescope. It's a strange radio telescope. It observes the sky at low frequencies, which range from 10 megahertz right up to 240 megahertz. So that's either side of the FM radio band. And it looks strange. The science that we receive is strange, but it gives us a real different insight into astronomical objects. And at the beginning of the talk, I'll try and give you a background as to where this all came from as well, for those of you who may not, who may be new to astronomy, to just bring you up to speed over a few centuries to how we got to these strange-looking radio telescopes. A little bit about Dublin Institute for Advanced Studies as well before we start. It was founded in 1940 by a man you may have heard of, Eamon de Valera. Dev, while not leading revolutions, was also very interested in physics and mathematics and astronomy. And at the time, in 1940, he attracted Erwin Schrödinger to Ireland from Europe, where he was really finding a difficulty with Nazi Germany and so on. He came to Dublin and he founded the theoretical physics division of the Dublin Institute for Advanced Studies. Nowadays, we're spread across central Dublin and also on the M50. We have Dunsink Observatory on the M50, just about 10 minutes from the airport. And then we have these lovely old Georgian buildings, and I'm not sure how lovely that 1960s building is, but we also have that building. It's about 120 of us all working on in the physics area, in geophysics and astrophysics and theoretical physics. And it's exclusively a research facility. In astrophysics, we have a strong group of people. There's about 40 of us. There we are in Dunsink Observatory, just beside the airport. And there's people from all over the world here. There's Italians, there's going to see Americans, there's Czech Republic, Russia, Georgia, and where else? Yeah, Germany, and so on. So a great mix of international people who are all here to work on the different projects that we work on, and they range from projects with the European Space Agency to NASA, and also we're delighted that Ireland joined the European Southern Observatory finally in the past few years. And we also joined the International LOFAR telescope, the topic of this talk this evening. So hopefully the group continues to grow over the next number of years and new research continues to come out. I don't know what this guy here is doing with the big grin. That's Owen Carley, an expert in solar radio physics. Okay, well, I guess all of us in the group are concerned with the night sky and trying to understand what's going on in the night sky. Some of us work on star formation, trying to understand the origins of stars, how they're formed, where they are formed, and also the conditions that give rise to the formation of planets as well. And that's Professor Tom Ray's research group works on that. They use things like infrared astronomy and also radio astronomy to study star formation, particularly in our own galaxy. They're also interested in astrophysical jets, these enormous jets of particles that can come streaming out of the poles of dense objects, collapsing stars, right through to black holes. I myself am most interested in the sun, in one particular star, and I'll talk a little bit about that as we go on. But I guess we're all interested on this call on the night sky. And even if, you know, to me it does many things. As a scientist, I want to understand it, but as a human being, I also find it terribly beautiful to look up. And no matter what, every single time I do look up at the Milky Way, I think there's a sense of mystery, a sense of wonder about how it's made, where did it come from, how long has it been out there, what are the stars made of, what are their temperatures? Very, very simple questions that actually a kid would probably ask you. But in order to make these discoveries, you really have to go back to a technological innovation. And I think in this talk, you'll see that astronomical discoveries follow technological innovation. And actually, sometimes it's the other way around as well, because astronomy or astronomers need to see objects that are very faint, they're very small, they're very far away, they're very small at the sky. So we drive innovation in new cameras or new telescopes, but also new innovation happens in terms of, say, electronics in recent years or computing that also allows us to make more discoveries. But back in the early 1600s, the telescope was invented in the Netherlands, and Galileo was the first to really use it as a scientific instrument for studying the stars and the planets. And when he turned this small telescope, all that it is on the top, you have a lens, and then there's an eyepiece down the bottom, and this beautiful ornate stand here. But he trained it on astronomical objects on the sun, presumably with a card at the far end to project the image of the sun onto a card, and also trained it on Jupiter and Saturn as well. And here are some of his recordings. Isn't it amazing how beautiful this picture is here on the left-hand side?
No, we're on bang on time.
I think if everybody can mute their sounds there, I'm hearing some people coming through. Please, just don't disturb everybody. So this is a beautiful picture, series of images taken by Galileo. And what you'll see is a sunspot working its way across the sun. And actually his conclusion was that the sun is not a simple object, but it's rotating and it has blemishes on it. And we know that these are sunspots. And actually every day since then, we have been recording the positions and the properties of sunspots as they track themselves across the sky. Actually, anybody who's interested in following the sun, if you check out solarmonitor.org, you can follow the sun in real time. And actually there's a lovely sunspot up on the top left, or the north east of the sun that we'd hoped would produce some solar flares, but fingers crossed it will. Of course, you guys in up the north coast, if any of you are up the north coast, can have the best chance of seeing an aurora that might be associated with that. But we'll see what that sunspot does over the next couple of days, and maybe in a week's time it might produce a flare. We'll see. Also on the right-hand side of this picture, you can see Jupiter, and over the days he was able to see that these three little pinpricks of light, which turned out to be orbiting Jupiter, so Io, Ganymede, Callisto, and Europa, he was able to track these and see that they were moving. But what it meant was that we were no longer the center of the universe, and things revolved around the sun was moving, and things revolved around other planets. And it put human beings outside their position of thinking that we were the very center of the universe. And this, of course, got Galileo in some trouble. If we jump forward to the next kind of big jump forward in astronomical instrumentation, Herschel in England, in Slough, built a telescope that was 40 feet long. And this telescope, you can see a gentleman down here posing with his top hat and so on. But you can see this telescope here, 40 feet long, and with a large mirror inside it, down at this end, and then an observer's box. But with this telescope, he was also able to make discoveries. Now, the telescope, all of the innovation around the mirror, around pointing it, around keeping it stationary, in order to make these drawings was a real challenge at the time. And it was a difficult instrument to use and required a lot of observer skill. So any of you who've used a Dobson telescope, that's not even half the battle. So these are some of Herschel's drawings, and he was particularly interested in, actually at the time, people were particularly interested in these objects in the sky called nebulae. And the nebulae, as you can see, are cloud-like structures in the night sky. They weren't pin points of light like a star may appear, or a smeared out piece of light like a star might appear in a telescope, but rather these were extended diffuse objects in the night sky. Actually, I think that's a comet number 2, but the other ones are all what we know to be galaxies now. And at the time, they didn't know if they were inner galaxies, if they were close, or if they were far away outside our galaxy. And that question was a major problem. Also, they weren't sure what they were made out of, and they also weren't sure what were their stars making up these nebulae. Now, that came to an Irishman called Lord Rosse, William Parsons, who was the 3rd Earl of Rosse at Birr Castle in County Offaly. And he did a couple of things. Number one, he was born to be an Earl, so that gave him a little bit of an advantage. And also he married very well as well. So not just very well, but he married a lady who had a lot of money. And he built with her, Mary Parsons, built this enormous telescope in County Offaly, which still stands there today. And quite an amazing object it is to see even today. As you can see, this telescope, actually, the aperture at the top brings light down to the very bottom where there's a speculum mirror, and the mirror is about 6 feet in diameter, or 1.8 meters in diameter. I think it's 16 meters long. The observer then goes into this observer's box here, or if you're near the zenith, you go to this gallery up on the top, and you can look through an eyepiece. It's a Newtonian telescope. But with this great Leviathan telescope, or the Great Telescope, as the current Lord Rosse prefers to call it, because the Leviathan was a little bit of a kind of a slag on it, calling it a monster of a telescope. But he made discoveries, and this was the discovery that the 3rd Earl made. He was able to see that these nebulae that Herschel was not able to resolve actually had structure. There was whirls in it, and you can see the immense detail that he was able to see. And also there seems to be an interaction between an object in the center of the image, the black dot, and the object on the right side of the image. They seem to be interacting, and he called it the Whirlpool Nebula, and he didn't know they were galaxies at the time. But his conclusion of that was that they're distant. They must be very distant from us, and they must be very dynamic. And it turns out that he even used a spectrometer on the Great Telescope, although there's little record about what he saw with that spectrometer. He certainly took a prism up to the telescope and had a look. And with the prism, you can tell if things are gaseous or whether they're solid. But here's a contemporary picture taken with the Hubble Space Telescope, and if I blink back and forth, you can see the kind of detail that he was able to resolve. So that image is from 1845. That image is from about the year 2000, or actually the 1990s, if I read my own slides properly. And what you can see is all the structure in there, which the 3rd Earl of Rosse resolved. So an amazing discovery that's known the world around. The Great Leviathan Telescope is world renowned, and the discovery of the Whirlpool Galaxy is known the world around. Of course, the telescope had to be beaten eventually. And this gentleman here on the left-hand side was wonderful at raising funding, and he also had some good ideas. And so ideas and funding were what led him to build this telescope, which has a 100-inch mirror in it. And so this was the next step forward. And this was in the late, well, about 1917, 1918, this telescope, and this photographs here from 1920. But this telescope was built by Hale. And with this, then more discoveries were made. And Hubble used this telescope to look at galaxies. And what he did with the galaxies is he was able to work out how distant they were with a thing called a Cepheid variable, a kind of star that's a standard candle in the night sky. But he was also able to measure the Doppler shift of these, which tells you their speed and their direction. So not only was he able to work out how far away they were, but he was also able to work out their speed. And in this plot here on the right-hand side, it shows how far away things are and how fast they're moving. And you can see that the farther things are away, the faster they're moving, and near things are moving slowly. But the conclusion of this was that the universe was bigger and the universe was expanding. And so you go from Galileo, who's discovering things in our solar system, through to Herschel, who's beginning to peer outside our galaxy and not knowing what the structure is, through to the third Earl, beginning to resolving the spiral arms of galaxies, and that the universe is much bigger and maybe there are other galaxies out there, through to Hubble. And each one of those discoveries came through the creation of a bigger and better telescope that was more sensitive and better angular resolution, i.e. could see smaller details in the sky, but also could see fainter objects as well. Now, it was Stephen Hawking, I think it was his publisher, said, for every equation you put into a book, you're going to lose half your audience. So I hope that doesn't hold in my talk here. But for those of you who like equations, and I do like equations, I grew to love equations despite hating them in school and finding them really challenging. In college, I just got better at them, but now they're part of my daily life and part of the language of astronomy. But what this equation says, and this is the Rayleigh criterion, it is called. And what it says is, on the left-hand side is delta theta, which is the size you can see. So it's big things or small things. So can you see big or small things? Well, if you want to see a small thing, you must have a big telescope. And that's what the D is. That's the diameter of your telescope. So if you want to see small things, you need a big telescope. But if you want to use radio waves, which are very long wavelength, then that's a real problem, because you got to get a bigger radio telescope. You got to get a bigger telescope. So this is a real problem in astronomy, in radio astronomy. And in radio astronomy, our waves can be meters in wavelength. So the light that we see with our eyes are hundreds of nanometers. So a nanometer is 10 to the minus 10. Let's say that again. It's a billionth of a meter. But when you're at a radio telescope, it's centimeters through to meters, through to tens of meters. So if you have tens of meters, then you need a really big telescope, and not just one that's 100 meters across or 100 kilometers across. You may need something that's 1,000 kilometers across to actually see small things. And if you could get a telescope that's the size of the Earth, then you can see even smaller things, and we'll come to that later on. But this picture on the right-hand side then shows you how this works. And imagine you had two stars or two galaxies at a great distance away from you. Well, if you only had a small telescope, you wouldn't resolve them. You just see a blob. And the more funding you get and the bigger your telescope, the further apart you can separate them, and you can see small details with a large telescope. And that's the drive in astronomy, to build bigger telescopes that allow you to see fine detail on the sky, but also to see faint detail as well, because a telescope is just a light bucket. It collects photons and allows you to see these fainter objects. This great telescope just outside Manchester, if you ever fly into Manchester Airport, you see this telescope, the Lovell telescope in Jodrell Bank, built just after World War II, with a lot of the technologies that were invented in World War II for spotting aircraft coming over the horizon with radar. But with the bits and pieces left over from that, astronomers in England really made some giant leaps forward, and likewise in in Australia as well. There was a huge burst in activity around radio astronomy, actually, and you know, with regard to innovation during the war, of course, NASA immediately hired lots of the people who knew about V2s from Germany as well. So some positive out of war, I guess, is the lesson there. But anyway, this telescope is probably as big as you can get for a steerable dish. And you can see there's a door. Where's their door? There's a door just down there to give you an idea of scale. And every time I see this, if you ever see this place pointing up at the zenith, you know, a human being is like that little dot down here. And I always think that Red Bull or something should see if they can get sponsorship to have a tournament where they put skateboarders on this. But I'm sure that Jogger Bank would completely object to something like that. But this telescope has a big diameter and it allows you to see small things. But that's about it. You can't, the engineering just can't, gravity is just going to win, and it costs too much money to get a steerable telescope. And this is where the next innovation came with a kind of telescope, radio telescope called an array or a phased array. And a phased array is really probably the ugliest radio telescope that you could possibly build. Very cheap to build for the most part. But really what you do is you get small, cheap whip antennas or wires, spread them across a field or a number of fields, hook them all up with coax cables, the kind of cables you have at the back of your TV, or at least used to have at the back of your TV, bring them into an amplifier because the signals are weak, and then combine the signals together. And with that, you can make images. And if you want to get that equation, if you want to work with that Rayleigh criterion equation where delta theta goes as 1 over d, the diameter, you could get d to be the size of England or the size of Europe or the size of the Earth and see very small objects. Not only can you see, you know, an arc minute on the sky, which is, oh, what's that, a finger at arm's length? A finger at arm's length, I think it's about, no, that's a degree, excuse me. Yeah, that's a degree. But you want to get down to arc seconds. And arc seconds is pretty good, but with a radio telescope, you can get to millionths of an arc seconds, to milliarc seconds of resolution on the sky. So you can see really, really small objects with a radio telescope. And this lady here was one of the early innovators in that. This is Jocelyn Bell Burnell, of course, from County Armagh in Cambridge, where she built, with others, of course, a large radio telescope that helped her and collaborators and her supervisor to detect a pulsar, which went on to win the Nobel Prize. Of course, we all know that unfortunately Jocelyn did not win the Nobel Prize, but in my feeling, in my opinion, she should have done. All right. So with these kind of telescopes, Jocelyn was working in Cambridge, but in the 1990s, an Irishman actually from Dublin was working in the Netherlands, and he'd be working in the Netherlands his whole life as an astronomer. And he wrote a proposal with others to build a radio telescope. And he had an idea that why not stretch this radio telescope the whole way across Europe? And it starts in the Netherlands, as you can see here. There's about 40 stations, I think it's 42 stations in the Netherlands. But there are stations out here in England, out in the east. Sorry, that's the west. Sorry, excuse me. On the sun, east is west and west is east. It's the opposite. So I'm continually confused by east and west now on the planet Earth. Anyway, so here in the west of Europe, we have the English station or the UK station. And then out here, we have Onsala in Sweden, stretching down to southern Germany. There's also a station soon going to go into Italy and then into Bulgaria, and stretching out also into Poland as well. So this telescope at the time stretched just over 1,000 kilometers. And at the core of the telescope, this is what it looks like. Clearly Dutch, you can see the water surrounding it, and it's very flat. But these elements here are the antennas that make up the telescope. And they convinced their government to spend nearly 100 million euros to drop these all across the Netherlands. Now, they could use these to detect radio waves coming from interesting astronomical objects, but they could also detect earthquakes with the fiber optic network and sensors at the end of that fiber optic network. They could also do seismic work. They were even looking at some environmental sensing, such as pressure and temperature as well. So it became a sensor network distributed right across the Netherlands. Now the antennas are very simple. They're very cheap, and they're very simple, should I say. And what you can see here is 4 wires with a grid at the bottom, a WAVN pipe essentially here, and then a preamplifier at the top. And radio waves come in from all across the solar system and all across the universe and are picked up by these antennas, which then go to the amplifier and get amplified, are passed down through coax cables here, in through the ground, and then are further amplified. But the thing is that they're so cheap, you can drop 10,000 of them across Europe, and each one of them will pick up a signal. And then when you add up 10,000 times the signal, you get a stronger signal. And also you can drop them across Europe. And when you drop them across Europe, you get a bigger radio telescope. So these are called the low band antennas, and they see below FM radio at 10 to 90 megahertz. Once you get to 10 megahertz, shortwave radio gets in the way. And also the Earth's ionosphere, you can't see through it anymore. So you've got to go to space, actually. And that's one of the reasons that there is one of these LBA antennas, or one like it, that was dropped on the far side of the moon by the Chinese in collaboration with the Dutch last year, the Chang'e satellite. The high band antennas are really strange looking. These are, there's a black tarpaulin that's pulled back here, but then inside it there are these what are called bow-shaped antennas. And they sometimes joke that the LOFAR system is like the the IKEA flat pack of radio astronomy, and you can see why. We built 96 of these in Birr in the summer of 2017. But in these you have 16 different crossed dipoles, and they see between 110 and 240 megahertz. And you pick up all the radio waves inside these, amplify them here, bring them into a central adder, and then the adder then sends them off for further application, and then sends them off all to a supercomputing center in the Netherlands. Excuse me. Now, we in Ireland were really interested in seeing these developments in the Netherlands, and George Miley, the Dutch-Irish astronomer, made contact with us and asked us would we like to join this international LOFAR telescope. So we got together a consortium that included Trinity and Armagh, UCD, Galway, Cork, DIAS, DCU, and Dublin Institute of Technology, supported by Birr, and started really a campaign to get this telescope funded. And also our friends at Birr Castle, who just are very proud of their heritage in astronomy, donated a field to us at €1 per year for, I think it's 20 years, to build this radio telescope. And that we did. Science Foundation Ireland gave us some funding, and then we went out in May 2017 and hired a whole group of young scientists and engineers. And really what we wanted to do with the project is not just do research, but also, open up astronomy, practical astronomy, to a whole new generation of astronomers, engineers, and computer scientists. And this group are from all across the place. People from, where do we have? From America, from UK, from Ireland, of course, North and South, and even one person from County Offaly as well, which was great to have somebody from County Offaly on the project team. We, of course, had to ship all of this equipment. We wrote a check to the Dutch astronomy group called ASTRON, and we then had to ship this kit. That kit there, you can see there's a shipping container at the back. That's €500,000 of computer equipment. So this guy, Ryan Milligan, who's based in Queens, was my first PhD student, it turns out. Was working in NASA at the time, and I gave him a ring and I said, Ryan, I know you have a truck driver's license. Any chance you'd like to drive a radio telescope from the Netherlands? And he says, I won't insult you by doing his accent. But he said, I'll do it, and off he went, and he drove the telescope across from the Netherlands across to Birr Castle. And you can watch a documentary that BBC Northern Ireland made called Space Truckers, and you can see Ryan listening to AC/DC talking about astronomy and keeping our telescope safe. He nearly missed the bus, or sorry, nearly missed the boat, so I would have killed him if he'd done that. But anyway, that's another story. So this is what we got these physics graduates, computer science graduates and so on to do. They worked in the muck in County Offaly, and they were a happy bunch. There were some tough times. It rained. It was the summer. What do you expect in Ireland? It rained. But they laid all of these cables, and you can see this is Aoife Ryan. Aoife is now a PhD student. This is Pierce Murphy. Pierce is now a PhD student as well. Anton over here is now a PhD student. Diana over here, she was the one who did all the cabling for the high band antennas and the low band antennas. There's 182 antenna cables in there. Actually, no, they're not. There's nearly 400 cables there because there's 2 polarizations. And she's now in Finland as a research fellow. But they built the telescope, and that was an amazing experience for these young scientists and young engineers and young computer scientists to get. They wore hard hats, high-vis jackets, and worked with the contractors. This gentleman here is from ASTRON, but I think he's from Afghanistan, actually. Am I right about that? I think it's Afghanistan. So that was interesting. And here's a Dutchman, and so on. And here they are. They built the antennas themselves, put them together, and tested them electronically, and then carry them out. And you can see them all very proud of it, bring it out and laying it to an accuracy of about ±6 centimeters on the ground. At the end of the summer, after some cheers and a few beers, we had a beautiful radio telescope, and here it is on a sunny day in July of 2017. You can see that it's raised above the ground. We raised part of it by a meter to stop. There's a river in behind these trees in the background that sometimes bursts banks. So this is to keep the telescope dry. And in fact, these are made out of tarpaulin. So the last thing you want is then floating off down into the River Shannon eventually. But these telescope elements in the foreground and the background, all of the data from them goes into this shipping container over here. And within the shipping container, data then goes off on a fiber optic cable at 3 gigabits per second off to the Netherlands to be combined with data from all across Europe. And we're delighted to see that we ended up on Google Maps, actually only quite recently. And you can see there's the Leviathan telescope in Birr. It was called the Leviathan of Parsonstown because Birr was called Parsonstown after the Parsons family at one point. And here is our wee telescope, as we call it. And when you zoom in on it here on the right-hand side, the white lines and X's are where ASTRON asked us to put them. So we got them right. So we're happy with that. And the Dutch were also quite happy that we've got them placed in the right place. The Dutch astronomers came over and technicians came over and did a test of the antenna in July 14th. This is Joe Macaulay. He was the main man for the build, and is our main our main technician at the moment. But this is what we saw, and to me there was lots of whistling and jumping around when we saw this. Turned on the telescope, all 96 low band antennas came on, and what you can see here is shortwave radio down here. This is low frequencies, about 10 megahertz. Clean. That's a little bump. That's just electronic effect of the antenna. The whole way up to 90 megahertz to FM radio when RT1 radio comes in and ruins our spectrum. But it was a clean spectrum. So Birr is very radio quiet, so you don't get much interference in Birr. Now, what we can also do with these radio telescopes, even in Birr with the telescope there, which is about the size of 2 football fields, is make radio images of the sky. This is a view from July 25th, just a week and a half after we turned on the radio telescope. We turned it on during the day or during the night, and you can see the Milky Way. This is the emission of low frequency radio waves from gas. This is a spur of material as well. And then you can see these objects. Now, when we turned it on and saw these and did a little bit of processing, we're quite nervous, you know, are they in the right place? Is anything backwards? Is north-north? Is south-south? So we immediately loaded it into Stellarium, which I'm sure some of you know, just to do it quickly in the field with a laptop. And there they were, Cassiopeia A, Cass A, Cygnus A, were both exactly where they should be, and the radio sources were there as well. So we were just terribly relieved. Cygnus A is a radio galaxy that's producing a lot of radio waves due to electrons moving out from a jet associated with it. And Cass A here is, excuse me, a supernova that occurred and is still glowing at radio wavelengths. So now we have a telescope that can look at the sky and then can zoom in on these features as well. But this is a big data telescope. You can also make images and movies of the sky. So this is the first time that images were strung together over a whole 24-hour period, watching the night sky and the day sky, the radio sky, rotating over the telescope at Birr. And so now we can do science. There's a lot of noise in there. Don't worry about that. That gets taken out in processing afterwards. This is just raw data. But you can imagine if there was a supernova, if there was a SETI source, if there was a solar flare, you'd see a flash. So what we've been doing ever since is writing algorithms to read in these data and process this data and remove the crud, the noisy bits, and then try to identify new sources. And one of the projects that we are working with is with the Breakthrough Foundation, who fund a lot of SETI research, looking for little green men from Offaly, I like to say. So wouldn't that be really cool if we found them? That's not particularly my research, I have to say, but a very interesting one if we do produce data that allows that to be found. Okay, so that's what Birr can do. We can see these, but I said to you that the reason we built this was not just because we wanted one in our own back garden. We also wanted to join into the large network of telescopes. And if you do that, you get a telescope that's 2,000 kilometers across. So you now have a telescope that can see very small detail, arc seconds, that's a couple of thousand kilometers across. So that makes it the highest resolution low frequency radio telescope in the world. So again, Birr has this connection to the biggest telescope in the world, but this time at low frequencies. If you do use the large telescope altogether, then you can produce images like this. And this is zooming in on Cygnus A, that galaxy that I mentioned earlier. And the red blobs on either side of it are what LOFAR sees. And then if you use an optical telescope, you just see a dot, which is actually a very active galaxy, which has a black hole at the center of it. But then you can combine that with X-ray images as well, and you see this cloud of hot material around that. So it's the combination of a big optical telescope, a space-based X-ray telescope, and a radio telescope together that gives you the complete picture of the black hole with an envelope of hot gas around it and jets of hot material moving outwards from it. And so this was a really fascinating new insight into astrophysical jets coming from from an active galaxy. And here's just a zoom in on that object again, showing where there is a black hole in the center of this and the X-ray emission, and then the jets of hot gas moving outwards. I can't give a talk without talking about my favorite astronomical object, which is the sun. And this is an ultraviolet image of the sun taken by a spacecraft called GOES, and it's the SUVI instrument on a GOES satellite, which is looked after by NOAA in the United States, and they use it to study space weather. But in September of 2017, just after we turned on the telescope, I-LOFAR, this enormous eruption occurred. And, you know, we really didn't understand how to use the telescope, but we got data. So it was really amazing. We've written a couple of papers looking at that. And, you know, the data may not be to everybody's taste. To me, I think this thing is beautiful. But what you can see on the left-hand side is an explosion happening where my cursor is. I hope you can see my cursor. and there's a shock wave moving out through the sun's atmosphere, and there's just radio sources everywhere. And with the International LOFAR telescope, you can see these radio sources, and you can see that they happen along the edge of the shock wave here and along the top of the shock wave here. And then with I-LOFAR and with the core of LOFAR, you can see that there's just all of these funny streaky features that we see. And these streaky features are produced by electrons. So the electrons are accelerated in the shock wave, and they go out through the corona, out into space. And we can say how fast they're moving. We can say where they're accelerated. We can say how they're accelerated for the first time. And it's the resolution, the sensitivity of LOFAR that really gives us that. And this was our first paper, actually, which was published in Nature Astronomy by Diana Morrison and a large team. Okay, Diana, as you saw in pictures previously, was one of the on the build team, and is now a postdoc in Finland. Okay, we can do lots of other things with the telescope. I apologize for how busy this plot is, but I wanted to just give you a sense for how deep the analysis goes. What you can see on the top right are these kind of a rubber band kind of contours of different colors, and they are taken at different frequencies, and they show radio bursts and where they occur in the solar atmosphere. On the left-hand side is a spectrum. It shows things going up and going down, is what you can learn from that. And then the things at the bottom, the big hairy balls, I guess, is what they look like, are where the things are and how they relate to theoretical models. So you have a theoretical model of the magnetic field, you know where the shocks are happening, and then you know where these electron beams are moving upwards and downwards. So very, very detailed, complicated physics that we can tell about the sun that we weren't able to tell before. So, you know, an amazingly exciting period for us since we got those data. Of course, with our close connections with Jocelyn Bell Burnell and radio astronomy's close connections with pulsars, the first, you know, one of the first things we wanted to do is, can we hear a pulsar? And, you know, of course, the third Earl of Rosse named the Crab Nebula. He thought it looked like a crab, and we now know that it is a pulsar. In fact, it pulses at optical wavelengths, and people sometimes wonder if he saw it. I doubt if it's just on the limits of what's observable. But we then turned I-LOFAR towards this pulsar, which is very romantically named PSR B0950 plus 08, and it just saw these pulses. So this is nobody was wearing earphones like in the Contact movie to listen to this, but in our data analysis, we were able to see these pulses. And the pulses come from a very dense object. So a neutron star, 10 kilometers across the diameter of Belfast, really, but rotating really, really quickly. And you can tell how quickly it's rotating. See these pulses over here? There's 5 seconds apart between ticks, and you have multiple pulses in that. So a pulse every second telling you about the rotation of that pulsar. And every time this beam here, which has electrons on it, passes or is directed towards the radio telescope, you see a pulse. And by looking at those pulses, you can test Einstein's general theory of relativity. You can look at electron acceleration on a huge jet. You can use them to test time and how time varies in the universe. So they can be extremely useful. And so we have many more observations. One of my graduate students, David McKenna, is currently working on those at the moment. And he's seen giant pulses coming from the Crab Nebula, really exciting result that we're currently writing a paper about, working with the Square Kilometre Array scientists with Evan Keane in Manchester. Of course, I couldn't get through this talk without showing you some other beautiful pictures. This time of the familiar object. This is the Whirlpool galaxy that the third Earl saw. And this picture was created using LOFAR, and you can see that LOFAR is able to resolve the spiral arms. But with optical wavelengths, it's hard to say much more than, yes, they exist. You need spectra to say something about what they're made out of. But with radio wavelengths, you can tell things like brightness temperature, you can tell temperatures of the gas, You can also measure polarization of the radio waves and work out the strength of the magnetic field, the orientation of the magnetic field, where the magnetic field is. What actually this image was taken, it was actually made by David Mulcahy, who was again another Irish astronomer, so quite appropriate, working in Manchester. Here's a comparison between the Leviathan telescope in the 1840s with Lord Rosse's sketches, and then from Sean Mooney in University College Dublin with LOFAR. And you know, you may say, God, we haven't come very far in 170 years or so, but this is, you know, with radio wavelengths, very different, very challenging, and telling you a lot about the properties of the gas. We can tell a lot more about the physics of it. But also what's really nice in this is you can see emission around this area up here, which is gas that's being dragged between these two interacting objects and producing radio waves. And so this is the highest resolution and long wavelength image of the Whirlpool galaxy. So I'm sure the third Earl would be tickled to know that a telescope in Birr Castle is again making contributions to our understanding of an object that he named. At the center of these galaxies, I should have just mentioned here before I move on to that, has to be a very dense, a very massive object. And it's long been thought that there has to be a black hole at the center of those. Now, when I was an undergraduate, when I was a PhD student in the 1990s, these were the things of, you know, pop science books and really complicated general relativity, and of movies, of sci-fi movies. The theorists told us that, you know, there was this thing called a singularity at the center. There was an event horizon where light could no longer escape from. There was an accretion disk of gas falling into this dense object, and there was a jet of relativistic particles moving outwards, producing radio waves. But it was almost the thing of sci-fi movies and intellectual or theoretical curiosity. And with optical telescopes, you could see this kind of thing. It was really challenging to see anything that looked like a black hole or evidence for a black hole. With LOFAR, though, LOFAR was able to see that what the optical could not see. It could see this huge envelope of hot gas with what looked like an ejecta of hot gas coming from a dense object, creating this enormous bubble of gas in the night sky. And again, this quest to see smaller detail prompted another radio telescope called the Event Horizon Telescope. And if LOFAR is the size of Europe, then the Event Horizon Telescope is the size of the planet Earth. It can get you across 10,000 kilometers. And with telescopes in the United States, in South America, in Europe, you can combine them all together and make detailed images of these objects. And this was the quest to see these very small objects. And the object that they looked at was M87 because it was suspected that it had a black hole at its center. It had a jet of material which had to have been accelerated by a very energetic object. And if you zoom in on that even more, with conventional telescopes and conventional radio telescopes, there was just this blob of material in there. You zoom in every more, just not seeing anything. And again, wispy material and maybe slight evidence for a black hole. And as technology goes forward, more and more and better telescopes are created. And this image, I just think, sets the whole scene for one of the greatest discoveries of the past decade, in fact, of maybe the past number of decades. What you'll see here is the LOFAR observations showing you 100 seconds, 100 arc seconds across the sky. Zooming in with the very large array, showing the jet, then zooming in again with the VLA, showing you 100th of an arc second, and then with the Event Horizon Telescope, showing you a black hole, showing you the hot gas that, or the light that doesn't make it into the central black hole object. So with LOFAR and with the Event Horizon though, telescope and with the other telescopes, it just gives you an insight into these amazing objects. And this is really what it looks like. So you've got the Event Horizon, you've got the black hole or the shadow of a black hole, and you've lens light from the accretion disk bent around it. This is my advanced PowerPoint here. May not be exactly correct, but it ain't bad. It gives you an idea for what you're seeing, how to compare the cartoon to what we saw with the Event Horizon Telescope. So maybe a Nobel Prize to come from that. Of course, I'm just name dropping here. This is Chris Hadfield. We had him in DIAS the day that this was announced, and had great fun chatting about these weird and wonderful astronomical discoveries with Chris talking about the telescope. So here ends my story. I hope I've given you an insight into the trials and tribulations of building a radio telescope and why we do it, and also some of the exciting new science that we've discovered. And really, for us, we're a new scientific community in Ireland. We have new PhD students that are training and being trained. So I feel that this is only the beginning of a journey for Irish astronomy. And I hope these young people go on to be more ambitious than some of the alphalas like myself, and try and build bigger and better telescopes and make more profound discoveries about the sun and stars and formation of stars and exotic objects like black holes. So thank you very much for your time and for listening to my talk, and I'd be happy to take any questions.
Thank you, Professor Gallagher, not Ferguson. I do apologise.
Not to worry.
First night nerves, you could say. And Terry has a query about the possible interference. If you're there, Terry.
Yeah, can you hear me?
Yes, fine. Go ahead.
Hi, Peter. Thanks very much. Fascinating talk. Really glad to get you at last. I'm just wondering, do you have an agreement with Offaly County Council and perhaps also with Galway County Council, because Birr's quite close to the border there, to keep the Birr region radio quiet?
Yeah, isn't that an interesting one? So low frequency radio telescopes, for everybody else, don't like nearby electronics. They don't like wires and cables, and they don't like sheep fences, electrical sheep fences. They don't like wind farms either. So the wind farms have a generator that can produce sparks that can cause interference. And also even the blades themselves can cause interference. So we have not an agreement, but we have submitted to the planning office a zone around Birr that requires the planners to take that into account. Maybe not requires, that might be too strong a word. But they certainly have to talk to us about what's possible. This is a really difficult one. The Midlands have lovely laminar airflow across them. They're great for wind farms. So, I think it will be slightly contentious in the years to come, and it's a real worry for us. In the Netherlands, they built, actually a number of wind farms have been built within 5 kilometers of LOFAR, and they've been able to deal with it by having a prolonged discussion with the developers and doing a lot of testing and trying to mitigate it engineering wise, and then for particular observations getting the operator to turn off their wind farms. So it's just a real challenge that we have to deal with. Yeah, good question, Terry.
I was just thinking, we of course in visual astronomy have to deal with Irish weather. It doesn't bother you so much, but also I was just thinking the Starlink satellites, which are a curse for every other professional astronomer on the Earth, they don't bother you either.
Okay, yeah, well, that's interesting. So, this is ideal for Irish climates. We don't care about rain, we don't care about snow, we don't care about sunshine. We're fine. We can see through the clouds. So it's good with that regard. Satellites we do see. We can see airplanes from time to time. We see over the horizon radar, military radar sometimes. The constellations that are going up are a real worry for us. We do see them. I don't think it's as bad as the streaks that you see in optical. But once they start broadcasting like a gigahertz, let me get this right. Lower wavelength radio telescopes are going to suffer in the so-called L band, so microwave. So yeah, it's a real problem. And without any protection by international treaties or governments, you know, it's a free for all and a real concern.
Okay, thanks.
Somebody asked me a good question after all that, Terry.
Nobody else is coming in. How do you link in, or can you link in or overlap with things like the LBA and the SKA?
The SKA, so SKA is the Square Kilometre Array. It's a €1 billion project being built in Africa and Australia. Really, the technology and the science that we do with LOFAR is a stepping stone to the Square Kilometre Array. So we learn a lot with LOFAR that we'll then use with Square Kilometre Array. Even handling the data, it really is challenging. We've how many hundreds of terabytes of data. LOFAR is producing petabytes per year, and SKA is going to produce that per day. So it's just going to be murderous to deal with. So we'll learn a lot about it, but there will be an overlap as well where we can coordinate observations from Europe and Africa. So that'll also produce some interesting stuff. I think in Africa and Australia, they're going to have less radio interference. Actually, that's one point that leads on from your other question, Terry. So they should be even more sensitive. But Ireland is still the lowest interference site in the network. We're keen to keep that the way it is.
Yep, that's great.
Professor, I'm just looking at your slide with the map showing the various locations. Do you know off the top of your head or exactly the furthest distance between any two of them?
Yeah, the Birr one to Bowdy is the way you pronounce it there on the right-hand side, I think is just under 2 megameters or 2,000 kilometers.
Guessing around
and I was just on a teleconference, a Zoom call. This is my 4th Zoom call today. I was on a Zoom call this morning with Bulgaria involved, and they are hoping to build a radio telescope in Bulgaria in the coming years. And I measured it this morning, the distance between Birr and Bulgaria, their site, and that's 2,500 kilometers. So you can see you can go from 2,000 to 2,500 kilometers. So you're really increasing the baseline and hence the spatial resolution by stretching out into let me get it right, Eastern Europe. And actually there's a lovely Irish connection there that the new Irish ambassador in Sofia, her son is doing a PhD in LOFAR at Dublin Institute for Advanced Studies. So we have a nice Irish-Bulgarian connection there as well.
You mentioned the Chinese probe on the far side of the moon. Do they have a relay satellite in orbit? I can't remember.
Yeah. There was a lander put down and then an orbiter as well. And it's like a repeater that you might have at home. It's interesting. Heino Falconer is the PI for that, and he was very much involved in LOFAR. He was one of the lead scientists on the Event Horizon telescope, and he then was involved in putting the antenna on the moon. And I wouldn't be surprised if his name pops up and the Nobel Prize in the years to come. So if you want him to speak, now's the time to get him, because it'll be impossible if he gets the Nobel Prize.
Keep that in mind.
Yeah, but it's interesting though, the far side of the moon, even in the 1960s, people were proposing putting radio telescopes on the far side of the moon to get away from radio interference. And there's an interesting low frequency radio telescope that's just being funded by NASA, which is a network of CubeSats. But basically you deploy all these CubeSats with antennas on them and fly them as an array. And then you can get them far apart in space and bring the signals back down, correlate them and make images. And you can do that at really, really low frequencies, much lower than LOFAR can do. So I think it's called Sunrise and is the name of the telescope. So there's lots more that can be done in space now with these, but you've got to get your satellites to be stable. They've got to be pointed stably. You've got to know, very accurately how far apart they are and where they are. So it's a real challenge. But I think it's the new frontier in low frequency radio astronomy, is going to the moon and going to space like that with flying arrays of CubeSats. And the Chinese are also planning on doing that, and everybody's looking to get to the moon as well.
Is there any data coming back from the Chinese site as yet?
Yeah, I've heard that there's data coming. Listen, I'm not 100% sure of the other scientific instruments, what's being returned from those. I believe when they turned on the low band antennas, there was a lot of noise in them. Apparently, it was from the rover, and the actual rover was producing radio frequency interference, but they dealt with it, and apparently they're getting nice spectra at the moment. But I haven't seen anything published. So they're clearly working hard on trying to make things pretty, as you do once you get the data. It's only half the battle.
Yeah. Michael Murphy has a question which leads on nicely from that, with earthbound cars. Michael, are you there? No, well,
yes, I am.
Go ahead.
No, just talking of Mr. Musk, it got me thinking, will electric cars cause problems as they become more numerous? Are they better or worse than petrol or diesel cars, just in terms of the radio interference?
Isn't that interesting? Yeah, absolutely. So I'm afraid I'm not buying a Tesla anytime soon. I did like the sound of that electric DeLorean that Queen's built actually at one point. But no, we couldn't have one parked beside I-LOFAR. The charger, anything that converts AC to DC or DC to AC is problematic, because there's a chopper in there that chops the signal, and so taking an AC from the grid and converting it into DC for charging a battery, you're going to produce radio frequency interference. So I'm not going to be able to park my Tesla anytime soon beside LOFAR. Now, if they're going past the castle walls, they're probably okay, and they're not charging anyway. But yeah, it's a good question. Actually, just an interesting one there about we put a magnetometer under the ground in Armagh Observatory, and the reason we put the magnetometer there was to measure the Earth's magnetic field and see it varying as a result of geomagnetic storms, and hence the aurora. And we built it beside this bungalow in the observatory, but they soon afterwards opened up a parking lot beside it, and people started coming to work and parking their cars there. And a big chunk of metal beside a sensitive magnetometer, we could tell when people were arriving and leaving for work. So we could see people arriving at 5 to 9 and leaving at 5 past 5, and we couldn't identify the car and help the director, unfortunately.
Terry, you have the follow-up. You want to go ahead?
Yeah, I'm just wondering, you're extending the network a lot east to west. Is it better to have better extent that way than north to south?
Yeah, there's, listen, the geography of Europe has determined a lot of that, rather than us sitting down and saying we'd rather an east-west baseline than a north-south baseline. But there is, when there's a thing called, you could do a thing called rotational synthesis. And what you do is you just allow the Earth to rotate, and and then you can basically use that baseline. So east-west are better than the north-south, but yeah, it's a political thing, or not a political thing. It's just the shape of Europe has determined it. But there will be one going down to Italy, as I said earlier, and it'd be great to get another one up north as well.
Right, thanks.
Are there any more questions? Anybody else?
Could I ask a question?
Who's that?
Jerry Davidson.
Go ahead. Okay, go ahead.
Okay. Absolutely fantastic. I must say, very, very enjoyable indeed.
Thank you.
And I'm sitting here with dozens of questions in my head, but one that popped into my head was one of the frontiers of science and astronomy now they're focused on exoplanets, and the resolution is a big factor there, identifying exoplanets, but to actually see detail or get information at that ultra resolution, where would the radio telescopes, be able to get information on that?
Yeah, that's a really good question. We're not great at it for some parts. The French at Nancy, just south of Paris, have built a super LOFAR station, and their whole dream is, actually you shouldn't call it a dream, their whole science goal is to detect exoplanets with LOFAR. And the thing is that an exoplanet with a strong magnetic field will emit copious amounts of radio waves. So if you think about, if you've ever heard of Radio Jove, which is, you put up a long cable in your back garden, hook it up to a small amplifier, and you'll see Jupiter. It's just so bright at long wavelengths or at low frequencies. And likewise, if you want to find Jupiter-like exoplanets or Saturn-like exoplanets, you can use a low-frequency telescope, and that tells you about the magnetic field of that exoplanet. Now, it'll be more challenging to see an Earth-like exoplanet with a strong magnetic field. But if you're looking for life, what are the things that you want to look for? You want to look for something that's, not too hot, not too cold. You want to look for something that has a nice magnetic field to protect it from the stellar wind of the star that it's going around. You want it to have an atmosphere, and a radio telescope will help you with that, habitability question. But no, really good question, and I really feel that it's going to be, the next 10 years are just where the big discovery is going to be made in those. And it's funny that you say that, because when many of us on this call were young, even in the year 2000, we only had 9 planets. There was one kind of detected around a pulsar, and nobody really believed that. And then now we've 3,000, detected, and many, many more to see. And we're beginning to see rocky ones, smaller ones that are in the habitable zones. And then, also gravitational waves has been detected. And then black holes have been imaged. It's just been an amazing 20 years in astronomy. So what next? And I think the what next has to be habitability. And, we saw with Venus, was it last week or the week before, that seeing molecules that, might be produced by life or, or an exotic chemical process. Who knows?
Okay, thank you. That's super.
Yes, very welcome. Thank you.
And is there anybody else with any remaining questions? No, that would appear to be it, Professor. I would like to echo those thanks for a very interesting, informative lecture. And we can't be together, but we can certainly applaud together in the usual manner. I'll ask everyone to show our appreciation.
Thank you very much.
Thank you
for your virtual clap.
Well, that brings us to the end of our meeting, and just a couple of things to mention. Our next speaker.
Terry, where are we going for beer now?
Yeah.
Where are we going for a beer? I thought that was the tradition.
Oh, it's a virtual beer, unfortunately. Or you can drink Guinness and Prentice come from a black hole.
Right. Next time.
Next time, Peter, indeed. And we would normally be treating you, have treated you to a meal beforehand in the local restaurant here. I think we did that the last time you were here.
Absolutely.
But hopefully we will be able to get together face to face in the future, and we'll certainly treat you to something. So thank you.
Looking forward to it. I'll have to come back with some.
We do miss that.
Yep. Okay, Peter, bye. Thanks again.
Bye, thank you.
Just for everybody's information, I would remind you that if you wish to stay online, you can do so. The meeting is open-ended according to Paul. Just 2 closing things. Terry has obtained the services of our cows for our next talk on October 7th.